This video is a review of circuits for AP Physics 2. First, I'd like to mention just a few generic things about circuits. That is, current is the rate of flow of charge in a circuit. You can think of it as delta Q divided by delta T. And there are certain things that determine that rate of flow of charge, like the different types of elements that are in a circuit. But nonetheless, current is the flowing of charges in a circuit. And in order to have a circuit, you need a closed loop of conducting material that allows the current to flow. And typically in a circuit, it is a battery that provides an electromotive force, or an EMF, that allows the charges to move. Right? Now that we know a lot more about potential and electric fields, maybe you can appreciate that if what the battery is doing is creating a difference in potential between 2 points, maybe plus V and minus V, then it's creating an electric field within the battery and within everything in the entire circuit. And that electric field, if I were a charged particle, like an electron in that electric field, the presence of the electric field would cause me to move in a certain direction. And so essentially what the battery is doing is, in order to get the charges moving, in order to generate that electromotive force, is it establishes a potential difference that creates an electric field. In AP Physics 2, we start to talk about not only ideal batteries, which are batteries that have zero internal resistance, but we also talk about non-ideal batteries. And the way that this is typically modeled on an AP Physics 2 exam is they will draw a dotted line, a little box around the battery. And a non-ideal battery has some internal resistance. And what the internal resistance does is it causes there to be a difference between the EMF that is supposed to be produced by the battery and the voltage that would actually be measured on the two terminals of the battery. So in the picture, I have a battery that has an electromotive force epsilon and a little resistor next to it with a resistance lowercase letter r. If I measured the voltage outside the battery along the two terminals of the battery, I would get a number that is less than what the battery is designed to produce, that EMF. And the difference between those two numbers is given by the equation below. If you would like to know what the voltage would actually be between the two terminals of the battery, you take the electromotive force, that epsilon, which represents the voltage that the battery is designed to produce, minus the voltage drop due to the internal resistance. And maybe you recognize that I times R is a voltage drop. So epsilon is a voltage that the battery is designed to produce. I times R represents the voltage drop due to the internal resistance. And the difference between those two things is the actual voltage that I would measure. So it's not that there's a resistor inside the battery, but it's not a perfect battery, and so there's some internal resistance, and we can model that battery as having a little resistor inside of it. Clearly, resistance is another important quantity that we have to think about in circuits. In principle, for a given type of material, if you know how long it is and what the area of it is, you can determine its resistance. For example, if you have a cylindrical piece of material, then if you know its length and its radius, then you can determine the resistance. And the way that I would find the area of the material is, if it's cylindrical, is I would use the radius, and I would use pi r squared to calculate the area, or the cross-sectional area, of that material. The length can be easily measured, and the resistivity, which is represented by the Greek letter rho, R-H-O, resistivity is something that is a constant for a given material. So if you look up a table of resistivities online for copper or aluminum or anything, there is a value of resistivity that defines that material in the way that density defines a material. And you can identify a material by its resistivity as well. Resistivity is constant, but it does have some temperature dependence. So as something heats up, you should expect that the resistivity changes a little bit. One way to identify a material would be to do an experiment to measure the resistivity of it. And if the resistance, right, so let's make sure that we know the difference between these two things. The resistivity is represented by the Greek letter rho, and the resistance is represented by the capital letter R. So the resistance changes depending on the length of the area, but the resistivity is constant. And what I wanted to say was that since the resistivity is related to the resistance, and resistance is related to voltage and current, right? By Ohm's law, the resistance is equal to voltage divided by current. Then you could also set this equation for resistance equal to voltage divided by current. And if I set up a circuit and I make varying measurements of voltage and current, then I should be able to make a graph of voltage divided by current versus length divided by area in order to produce a linear graph where the slope is equal to the resistivity. And that is because the equation of a line is y equals mx plus b. Now in this equation there's no plus anything, but what I'm plotting on the y-axis is the resistance, or the voltage divided by the current, and what I'm plotting on the x-axis is the length divided by the area, so the slope of that line is very much the resistivity of the material. And so in comparing two different things, if I have two pieces of graphite, for example, then they should have the same resistivity even though they have different lengths and areas. But a material that has a longer length, so two pieces of graphite and one is longer, the longer one will have more resistance. Or if there's two pieces of graphite that have an equal length but one has a bigger area, the one with the bigger area will have a smaller resistance. Perhaps one of the most important tools that we have for analyzing a circuit is Ohm's law. Ohm's law relates the current, voltage, and resistance in a circuit. And really what it says is that as long as you are working with an ohmic material, O-H-M-I-C, an ohmic material, then if I make a graph of the voltage as a function of current, then I should get a straight line, and the slope of that line is equal to the resistance of the material. So some circuit elements are ohmic, which means that we can use Ohm's law, which means that if we made that graph we would get a straight line. But there are many circuit elements that do not obey Ohm's law. They're non-ohmic. And we can't know exactly what that graph is going to look like, but it won't be linear. Maybe it will curve up or curve down. But what's important is that even things that are non-ohmic might be ohmic for a certain range of currents and voltages. So for example, down here, even though on the right side of the graph some of those things were non-ohmic, they didn't follow that straight line, they all pretty much followed the linear trend at small currents. And so things like resistors and light bulbs tend to not be very ohmic because they heat up and then the resistance of the devices change as they get connected to a circuit. But maybe at small currents they don't heat up so much and they're fairly ohmic, so we could use Ohm's law to calculate the voltage or the current or the resistance. When trying to understand a circuit, you really need to understand the difference between series and parallel. In a series circuit, there's only one path. And hopefully you recognize that if I'm staring at the circuit on the left, the current will come out of the positive terminal of the battery and flow through this single path back through the battery. And for that reason, there's nowhere else for the charge to go. There's only one path, which means that everywhere along that path, the current is the same. So at point A, the current is equal to the point the current is equal to the current at point B, which is equal to the current at point C, which is equal to the current at point D. The current does not change as I move across the resistor. There is a voltage drop, but that does not manipulate the current. Everywhere in a single path, the current is the same. In order to find the equivalent resistance of a series circuit, all I have to do is add up the resistances of all the resistors. So if each resistor value is known, I could just add up those three numbers to find the equivalent resistance. And the reason why that's important is because more often than not, we need to know the current in the circuit. And in order to know the current in the circuit, I need to know the total resistance of that circuit. So maybe I'm given information about the voltage of the battery, and I'm given information about the resistors. I would add up the resistance of all those resistors, draw a simplified circuit where the equivalent resistance is known, and then I could use Ohm's law to calculate what the current would be in that loop. By calculating the current in that loop, I now know what the current is in this more complicated circuit. And opposite to what we're going to see with the parallel case, while series circuits have the same current everywhere, they do split the voltage. And so let's say that in the circuit above, the battery has a voltage of 9 volts. If each of the resistors has the exact same resistance, then each of the resistors is going to have a voltage drop across it of 3 volts. Now, if one of those resistors has more resistance than the others, it will have a larger voltage drop, and the ones with smaller resistance will have a smaller voltage drop. But in the case that we have a 9-volt battery and each of the resistors has the same resistance, that means the voltage drop across each of them will be the exact same. And because the voltage has to split up and use up all 9 of those volts in the circuit, each one has to have a value of 3. Now for the parallel circuit. Clearly, there are multiple paths, right? If the current comes out of the battery here, it has a choice to go through this top branch or keep going down to the bottom branches, and then again to go through the second branch or keep going down to the third branch. And so there are multiple paths. What's different about a parallel circuit is that in each branch of a parallel circuit, we have the same voltage, which means the voltage between points A and B is the same as the voltage between points C and D, which is the same as the voltage between points E and F. And because each one of those light bulbs is connected directly to the 2 terminals of the battery, which is here, right, where there's a potential difference delta V, what that means is between each pair of points A, B, C, D, E, F, they get the full voltage of the battery. And if you remember looking at a parallel circuit versus a series circuit, the light bulbs in a parallel circuit are typically much brighter, and that's because each light bulb would receive the full voltage of the battery, whereas in series, they have to split the voltage. Also, the equivalent resistance of a series circuit requires a little bit more effort to find. You might remember that 1 over the equivalent resistance for a parallel circuit is equal to 1 over the resistance of the first resistor plus 1 over the resistance of the second one. And so typically what we do is we plug in 1 over R plus 1 over R plus 1 over R into our calculators, we hit enter, and then we remember that we have to take the reciprocal of that answer in order to get the equivalent resistance. And so while in a parallel circuit each resistor or each bulb is going to have the same voltage, the current, as I showed with that green arrow up above, does split. And so we get a split current but the same voltage. One very important point is that in a series circuit, the equivalent resistance goes up because I'm adding them together, right? So if I have multiple resistors, the equivalent of those many resistors has a higher resistance. And in a parallel circuit, when I add up those resistors, it's as if their equivalent resistance has gone down. And the equivalent resistance has gone down. And the metaphor that I'll use to describe this, because it doesn't make sense, if I add another resistor to that parallel circuit, the resistance will go down even more. And so how come every time I open up a new path, the resistance is going down? The metaphor that you should think of is if you're driving your car down the street through construction and everybody has to go in one lane, then there's a lot of resistance. You don't get to drive very fast. But the moment the construction opens and there's an additional path, there's an additional lane that you can drive your car down, now all of the cars split into those two lanes and it's much easier for everybody to travel. And so for that reason, every time I add a resistor to a parallel circuit, I'm opening up a new path which lowers the equivalent resistance and increases the total current in that circuit. Two rules that we need to know about in AP Physics 2 for analyzing a circuit are Kirchhoff's rules. I'm going to start with the junction rule on the right-hand side because the junction rule is pretty easy to understand. What the junction rule says as a metaphor is, let's say we're at a four-way stop and there are cars approaching the four-way stop. The number of cars that enter the four-way stop is equal to the number of cars that leaves the four-way stop. So if there are cars coming in, the cars have to leave the four-way stop. So the amount coming in and the amount coming out has to be equal. And Kirchhoff's junction rule says that, but for currents. And so if we pick a junction, which is a point where multiple parts of a circuit come together, like right here, then the currents coming in have to be equal to the currents coming out. And for the point that I just drew, maybe this is point A, at point A, there are several currents coming in and coming out. First, from the battery, there is a current right here that is coming out, and I've called that I. So I represents the total current that's coming out of the battery. And at point A, there are a couple of currents that are coming out of there. There's I1, which goes to the top branch here. There's I2, which goes to the bottom branch, and then there's I3. So apparently, in this circuit, the total current is equal to I1 plus I2 plus I3. The sum of those three currents must add up to the total current. And another reason why I know that's true is because if I look at junction B, all of the currents coming into that would be I1, I2, and I3. And it is all of those currents added up together that needs to go back into the battery, and that current should be the same as the current that comes out of the battery, which is equal to I. So at a junction, the currents going in is equal to the currents coming out. Kirchhoff's loop rule on the left-hand side is a little bit more difficult to understand, but I don't know that it's any less difficult to actually apply and use. It's actually very convenient. What the loop rule says is that the sum of the voltage rises and drops in a circuit is equal to 0, as long as I go around a closed loop, and that's why it's called the loop rule. So what this means is, if I start at a particular point in space, let's call that point A, and I move from there to point B, to point C, to point D, and then back to point A. So I'm going in a loop of A, B, C, D, back to A. Then across each one of those circuit elements, there's a voltage drop. And that voltage drop can be used in the loop rule equation to write an equation that might be able to be solved for something. And so the way this works is, if you encounter a voltage rise, we'll call that a positive voltage. And if you encounter a voltage drop, we'll call that a negative voltage. And we'll set that equal to 0 around this closed loop. So what we do is the following. If I start at point A and I move across the battery toward point B, across the battery I would experience a voltage rise. And so I'm going to call that plus V. As I go around this loop and I get to this 5 ohm resistor, there's going to be a voltage drop across that 5 ohm resistor. So I'm going to call that minus, and I don't know what to write because I don't know the voltage across that resistor. But what I do know is that voltage is equal to current times resistance. So if I just figured out the current, I already know the resistance, I can just label that as I times R. So there's going to be some voltage drop equal to I times R that happens across that resistor. And the same is true for the next two resistors. As I move back to point A, there's going to be another voltage drop equal to I times R for the 10 ohm resistor, and another voltage drop equal to I times R for the 5 ohm resistor. And that should be equal to 0. Now, I have a 12 volt battery and a 5 ohm, 10 ohm, and 5 ohm resistors. This is a series circuit, which means that the voltage is split among those different resistors. The current is the same everywhere, but the voltage is split. And if you just think, I mean, we could try to calculate what the total current is and then start to plug in values. But one way that I could do this is I could say that the voltage needs to be split into 4 even pieces. And how do I know that? Because here I have 5 ohms, here I have 5 ohms, and then here I have 5 ohms twice. And so really, if I could divide the voltage into 4 even pieces, then I should know how the voltage will split up, sort of, without having to do all the work. And so if I divide 12 into 4 pieces, then that gives me 3 volts for each one of those pieces. So for each of the 5 ohm resistors, I should expect a 3 volt voltage drop. And for the 10 ohm resistor, I should expect a 6 volt voltage drop. And as you notice, 6 plus 3 gets me back up to 12. And so the full voltage of the battery is plus 12. The first resistor, that 5 ohm, is a 3 volt voltage drop. The second 10 ohm resistor has a 6 volt voltage drop, and the last one has a 3 volt voltage drop, which adds up to 0. And so it works out. The more practical way of maybe going about this would be to write a simplified circuit that looks like this. We have a 12 volt battery and a simplified circuit which has an equivalent resistance of 20 ohms. Right? 10 plus 5 plus 5 is 20. I could use the total voltage of the battery and the equivalent resistance to calculate the current. And then in my equation down below, I could plug in those currents and the resistance of each resistor, and I would end up with the same result. But practically speaking, one of those resistors is probably going to be unknown. And so for that reason, you can use the loop rule to write an equation like this to solve for that unknown resistance. Sometimes in thinking about a circuit, we are asked questions about power. The equation for power is current times potential difference. And by Ohm's law, we could make some manipulations of that equation as well. Since V equals IR, I could replace the current with V over R, which gives me V squared over R. Or I could replace the voltage with I times R, and I would get I squared R. And if we had a little bit more time to talk about this, we could show that for a given circuit element in a given circuit, that the power is directly related to the current that flows through that device. And so power is directly related to current. And because power tells me about brightness, this means there's a relationship between the current through a circuit element and the brightness. So anytime you're asked questions about brightness, you should be thinking about the current and you should be thinking about the power. The power dissipated by a light bulb, for example, tells me exactly about the brightness because that's where the brightness comes from. As charge flows through a light bulb, there is power dissipated by that light bulb, and we are seeing the power dissipated, most of it coming off as light. And of course, if you touch a light bulb, it's quite warm, and so some of the power is being dissipated as heat, but some of it's being dissipated as light, but we see that. Nonetheless, there's a direct correlation between power, current, and brightness. The main thing that was new to AP Physics 2 for circuits was the idea of putting capacitors in a circuit. And a capacitor is something that stores charge over time as the current flows. And so what this meant is the circuit started to be more dynamic. By having the capacitor in the circuit, when I close a switch, things are getting brighter and dimmer and the current flow is changing over time. And so it's a little bit more complicated to understand. Let's start off on the left-hand side. If I just connect an uncharged capacitor to a battery that has a potential difference delta V, then charge will flow in this circuit. Now, what a capacitor essentially is two plates separated by a certain distance, so it actually prevents the flow of charge. But it's if I connect the two terminals of a battery together, the charge wants to flow. And so what inevitably happens is, let's say I'm an electron that's right here, that would flow if there was a current, and I connect the two terminals of the battery together with a capacitor, that electron is going to want to move to this plate of the capacitor because it's repelled by the negative terminal of the battery and would want to move clockwise. Similarly, positive charge, if a bunch of negative charge is being accumulated on that right plate of the capacitor, then any positive charge is going to start to accumulate on this left plate of the capacitor. And that's not necessarily because the positive charge is moving. What it means that electrons over here would want to go this way. After all, that's how they accumulate on the right plate anyway. They go around and flow clockwise to get to that right side of the plate. And so I connect an uncharged capacitor to a battery, and what happens is the capacitor becomes charged. It starts to store some charge on its plates. And the current will continue to flow until the capacitor reaches the same voltage as the battery. So charge will flow until the capacitor has the same voltage as the battery. I could then disconnect the capacitor from the battery, connect that to a light bulb, and the light bulb would turn on because the capacitor has some charge stored on its plates, and so if I connect it, that charge can become discharged and flow across the light bulb, turning it on momentarily. Now the battery is designed to have, allow the flow of charge for a long time. The capacitor can only store a little bit of charge, and so the light bulb would turn on when I connect the capacitor to it, but only for a brief moment until the charge in the capacitor runs out. I would then have to reconnect it to the battery. So this is a fairly simple circuit, but let's look at the one on the right. The circuit on the right has a switch, a capacitor, and a light bulb all connected in one. Initially, if the switch is open, nothing is happening, but if I close the switch, then current will flow to this point. And at that point in time, the current has to make a decision. Those electrons have to make a decision. Do I want to go across the capacitor, or do I want to go down towards the light bulb? And what's going to happen is the charge is going to flow to the capacitor. And the reason for that is the capacitor is initially uncharged and doesn't have any resistance, but the light bulb has some resistance. For that reason, the charge is going to flow through the capacitor. And after some of that charge starts to flow on the capacitor and build up some charge, now there is reason for the charge to instead bypass the capacitor and go down through the light bulb. And so what happens? Step number 1 here. When the switch closes, current initially flows through the capacitor. Step 2. As the capacitor charges, more and more current flows through the bulb and it gets brighter. Right? The moment that capacitor reaches the full potential difference of the battery, now no current will flow in the branch with the capacitor, and all of the current will flow through the light bulb. And so it will become brighter as that capacitor starts to get charged. Now, this does not happen in the snap of a finger. Over time, more and more charge starts to get directed away from the capacitor and toward the light bulb, and so that way it gradually gets brighter. And you might imagine that while this is a parallel circuit, if I were to construct a similar series circuit that had a capacitor and a resistor, as the capacitor started to get charged up, if once the capacitor has the voltage across it of the battery, current can't flow anymore, then what that means is that if there is a light bulb and a capacitor in series, something like this, so here's the battery, here's the resistor, here's the capacitor, then the moment that capacitor gets fully charged, there will not be a current anymore in this circuit. The current will become 0. And so in a parallel circuit like the one I've drawn, the light bulb will gradually get brighter. And in a series circuit like the one that I've drawn, the light bulb will gradually get dimmer. In the same way that we came up with different rules for finding the equivalent resistance in a series and parallel circuit, we need to have equivalent or similar rules for finding the equivalent capacitance in series and parallel circuits. And it turns out that the rules are flipped. So for resistors, for many resistors in series, you add them up directly to get a greater equivalent resistance. For capacitors in series, each capacitor in a series circuit will reduce the equivalent capacitance, but luckily, even though the rules are opposite, we still use the same equations. So I will do 1 over C plus 1 over C plus 1 over C in my calculator, hit enter, and then I will do the reciprocal of my answer to find the equivalent resistance for a series equivalent capacitance for a series circuit. And for capacitors in parallel, if I have 1, 2, 3 capacitors in parallel, then the capacitance adds directly. I add the capacitance of each capacitor in parallel to make a greater equivalent capacitance. And again, the purpose of this is typically to take a complicated circuit and reduce it, make it less difficult to understand, so that way I can use the properties of that simpler circuit to calculate something for the more complicated circuit. And maybe this makes some sense, right? Since each of these capacitors are directly connected to the battery, each one stores the same voltage across its two plates. And for that reason, if it has a greater voltage between the plates, then maybe it can store more charge. Whereas in series, each capacitor stores some split amount of the voltage across it, therefore it can't store as much charge. There should be a relationship between the capacitance, the voltage across the capacitor, and the amount of charge it can store, and I think we're going to see that on the next slide. Lastly, I just wanted to remind you of a few equations for a capacitor. The first one, the equation that I just mentioned, and that is the potential difference across the two plates of the capacitor, the charge stored on each plate of the capacitor, and the capacitance of the capacitor. Now the voltage is measured in volts, and the charge should be measured in coulombs. But capacitance, remember, I haven't mentioned anything about it until now. Capacitance is measured in farads, right? And we've heard of like a an X number of microfarad or nanofarad capacitors. So F stands for farad, which is short for Faraday, and is the unit for capacitance. So as I said, the larger the potential difference between the two plates, the more charge it can store for a given amount of capacitance. And as I mentioned in a previous video, the capacitance of a capacitor is directly related to things like the area of the plates and the plate separation. So if the plates get bigger, the capacitance gets bigger. And that makes sense. If the plates are bigger, they can store more charge. And the plate separation has an inverse relationship. So the further apart the plates are, the harder it is to have a higher capacitance. And then epsilon naught was a constant, and so is K, but K represents the dielectric constant. It's a constant that represents the material that is between the two plates of the capacitor. And sometimes a dielectric is put in between the plates of a capacitor in order to allow the capacitance to be greater. Because if there's just air between the two plates, sometimes there's a tendency for the charge to spark across the air. But if you put a dielectric in between there, that is harder for the electric, if the charge, as the charge increases, then the electric field between the two plates can break down, and then there's a spark. And that's easier for air than it is for some of the dielectrics that could be put between the two plates to allow the capacitance to be higher and store more charge before breaking down. Lastly, inevitably, if there's charge being stored on plates like this, then there is energy being stored on the plates. And that's why if I disconnect a charged capacitor from a circuit and connect it to a light bulb, the light bulb turns on. If the light bulb's turning on, then there must be some energy stored on that capacitor that's capable of lighting the light bulb. And the amount of energy stored on a capacitor, that potential energy, is given by 1/2 Q delta V, where Q is the charge on one of the plates, and delta V represents the voltage between the plates. And I've said this a couple times now, but Q does represent the charge on one plate. So in a capacitor, the amount of charge on one plate is equal to the charge on the other plate, but Q in each of these equations represents the charge stored on one plate only. So you don't have to add up the charge on the two plates, just use the charge of one plate. And because of the equation on the top left, we could rewrite the equation. We could get rid of Q and express it in terms of the capacitance and the voltage, 1/2 C times delta V squared.